Tonight we're going to go over IP addressing. Now, IP addressing has many components. We're going to focus today on the fundamental logic that is used in IP addressing. So where do the addresses come from? What does it actually mean underneath the hood? And then we're going to talk about the methods of routing IP addresses, but only insofar as the structure of IP addresses that is used to enable internet routing. So when we start talking about IP addressing, we need to start from a very fundamental level here. So at its core, an IP address is a 32 character string of ones and zeros. That's why IP addresses are known as 32-bit addresses. Now, none of us in our lifetime will ever remember an IP address in its binary format. So functionally, what happens to an IP address is that we break it up into 4 groups of 8, and those groups are called octets. Now, each octet goes through a fairly simple mathematical process that we'll be dealing with in just a second. And we end up with this address where the numbers are between 1 and 255 for each of the octets. So one octet can represent a number from 0 to 255. Now, one thing that's a little confusing is that's actually 256 addresses because 0 counts as an entity. So in this case, we broke the 32-bit string into 8-bit octets, and then each of those octets was converted to decimal. And in doing that, we ended up with an IP address of 146.72.5.2. In this next section, we're going to go through the math of how that conversion happens. So the first thing we need to go over is the way that binary is converted to decimal. We have 8-bit positions. Each of those positions has a value. The furthest to the right has a value of 1. The second from the right has a value of 2. The third from the right has a value of 4. And they keep doubling until you get all the way to the furthest bit position on the left, which has a value of 128. The way we do this conversion is we then look at our bit string in this particular octet, and we say, okay, the 128, the 16, and the 2 bits are set to 1. So I'm going to bring those down and add them together. And that's where I get the 146 that is the first octet in our IP address. Let's look at the next octet. So in this octet, we have the 8 and the 64 set to 1. We carry that down, add them together, we get 72. So now we have 146.72 and .5. As you can see here, the 4-bit and the 1-bit are set, so we add those together to get 5. And then in the last one here, you can see that we have just the 2-bit is set to 1, so the last octet is 2. This is actually very straightforward, and it's only done for human readability, right? Computers will always think of it in that 32-bit string. The reason I wanted to show this to you is because now we're going to get into subnetting. So just to wrap up here, what this tells you is a unique entity on the internet. In order to get meaning out of it, we need to then extend that. As anyone who's ever worked on a computer or done anything knows, that next step we need is what is the subnet mask? And then via convention, we can infer what the default gateway is. So the subnet that we're going to be operating on here is 255.255.255.0. In the old days, this would have been called a Class C address. 256 addresses, because you're basically taking one octet, that last octet you're setting to 0, meaning that all of the 8 of those bits are reserved to represent a specific host rather than the network that that host is on. If we break that down into the octets, we can see that we have 255.255.255.0, which means if we then convert that down to the bits, each of those first 3 octets is all ones, right? We know that because if you set them all to 1 and then went through the process we just did, you would end up at 255. So we then pull those down and say, okay, this is the mask. When we look at this, we can see that the first 3 sets of 8 bits are set to 1. We write that out, and then we take that number, whatever the significant bits number is from each octet, and we add it together, and we get 24. This is classless interdomain routing. There's no difference between the top of this and the bottom. It's just a shorthand way to represent, instead of writing out 255.255.255.0, we just write that as 146.72.5.0/24. Now that .0 is what we call the network address. That address is what is sent out to the internet to say, hey, this network of 1 octet worth of IP addresses is here. That's a routing announcement. Someone is going to announce out to the internet that 146.72.5.0/24 is located here. So you can't use .0 as an address because it's the descriptor for that block of addresses. So now that we've got the /24, this opens up the chance for me to talk to you a bit about bit boundaries. Now, we'll get more into this when we get into the routing section because it's kind of important. But in your mind, just understand that if you take this 146.72.5.0 and you add 1 to that annotation so that it's /25, what you're doing is taking the first bit of that last octet and you're adding it to the mask. So now the mask is 25 bits long, which means that you're breaking those 256 addresses into 2 networks. So now you'll have 146.72.5.0/25, and you'll also have 146.72.5.128/25, right? So every time you go up an integer in the net mask, you're breaking the network in half. So at a 25, you have 2 128 address networks. At a 26, you have 4 64 address networks. At a 27, you have 8 32 address networks, right? Because each time you're moving the significant bit to the right, so you're shrinking the piece of the address that refers to the hosts, and you're expanding the piece of address that refers to the network. And each time, because it's binary, right, you're either going to have it, in this case, you're splitting it into 2, or if we go the other way and we say, now let's make it a 23, then what we're doing is effectively doubling it and saying now, I can't do that. It's the wrong bit boundary. That's good planning. So if we were going to have this as a 23, it would be 146.72.4.0/23. And that would mean that any address that starts with 146.72.4 or .5 would be within this one network announcement. So we would advertise 146.72.4.0/23, and the whole rest of the world would know to send all traffic destined to 146.72.4 and .5 to that location. I do want to touch on something called RFC 1918 space. These are the addresses that everyone watching this video will know, even though they don't understand why. But RFC 1918 reserved a set of addresses that anyone can use anywhere they want, but is not routable on the internet. So I can use these addresses within my house, at my office, I can use these addresses, but I can't go from 1918 addresses at my house to 1918 addresses in my office without going through routable addresses. Those addresses are not valid on the internet. And the two you're going to see the most often are the 192.168 networks. And that's normally what we've kind of grouped together and decided those are end user networks. So pretty much any router you get is going to come with a 192.168.1/24 as your internal network. The other one that's in common use is more reserved for business, labs, test networks. That's the 10net. And the reason is it's an entire old Class A, right? So it's a huge IP address space. So people like IBM can have all of their labs worldwide in the 10net space, but not have to reuse addresses, right? So they could choose to route all of their labs together so you get from one lab to any other lab, even though they can't outside their network get to those addresses. So that's why the decision was made that the 192.168 block, which is the smaller Class C space, that was used for small businesses or home users. And then the big reserved space, the 10net, which kind of traditionally been used for corporations or governments in their testing. You can't route that address space across the network, so you have to NAT it, network address translation, which is why on your home network, you'll have a 192.168 address. It'll go to your router. The default gateway will be .1 on that network normally. And then your router will have a single address assigned by your cable provider, your ISP, whoever. And every computer within your house will look like it's coming from that one, what we call public address on the router. So when my when my desktop, my gaming PC here, reaches out to connect to the authentication server, the server doesn't see my 192.168.1.3 address that is my PC. It sees whatever's on the public side of my router downstairs that my ISP gave me. I think that's probably enough for today. This was another one of those, I finished the graphics and didn't feel like writing a script, so I apologize for rambling a little bit. I hope you got some value from this. And again, a lot of this will make more sense. I think one of the next few videos I'm going to do is how does an Ethernet work? This foundational knowledge will be used and will make a great deal more sense. But for right now, really, if you remember anything, remember this page here that I'm going to show you again. The address and subnet mask. What the mask does defines the network versus the host, and then how the exact same information can be reflected using that 255.255.255.0 or the /24. All right, enough. I'm geeking out on y'all here. With that, I will let you get back to your time. Thank you very much. If you're new here, please like, comment, and subscribe. In that order, I'd love to hear any thoughts you have. Thank you.